Hey astronomy kids, this is Mr. Johansson. I want to teach you the fifth question on our astronomy final exam. And the fifth question, where we start really getting into how do we understand stuff about astronomy. Fifth question says, how does the spectrum of a star allow us to understand its chemical makeup? So that's what I want to do with you right now. All right. Best thing I could do probably is to show you a quick demo. All right, so take a look at this little box here. This is going to project a very high level of electricity, high voltage, I should say, of electricity through some of these spectrum tubes. And let me pick out a good spectrum tube for you to see right now. All right, that is a neon light. Well, if you were to put on one of these cool glasses, and you look at the neon light through that, well, you might be able to see through the cool glasses that the neon light turns into a bunch of lines. And kind of hard to demonstrate through the camera, but when you look at it on the spectrum, instead of seeing just one line, you see a bunch of lines in different colors. That's what a spectrum does, is it smears all this light out so you can see a normal range of colors. If you think about a normal spectrum, why do you have the spectrum that you have, a rainbow spectrum? Well, that's given off by an incandescent object. And an incandescent object, excuse me, an incandescent object is one that glows really brightly. It's hot. The atoms on it are hot. Let's think about the difference between a cold atom and a hot atom. If this is a cold atom, what does a hot atom look like? Hot atom is wiggling and jiggling. It's vibrating violently. The hotter, the faster it's vibrating. If I were to put my hand on the surface of water and vibrate it very slowly, what kind of waves would it give off in the water? Well, this is what we want to talk about. When you have an atom, which is a combination of charged particles, vibrating, it's accelerating back and forth. Anytime you have an acceleration of charged particles, you give off electromagnetic radiation. It's just like a hand in water bobbing up and down. It's going to give off little ripples. The hotter the atom is, the faster it's vibrating, the littler the ripples, the more energy those ripples are carrying away. So smaller wavelengths carry more energy. Now think about if I were blacksmithing, and I take a poker and I put it in the coal fire and I pump that up and get it really hot. I pull it out. It doesn't make, I still can't see it. Close to my face, whoa, that thing is really hot. It's giving off some kind of radiation, but my eyes can't pick it up yet. If I put it back in and heat it up, now the atoms are vibrating faster and faster. Finally, they're vibrating so fast. These are the longest waves my eyes can see. The longest waves my eyes can see. Well, what would they be? They would be red, that deep cherry red. Those are the longest waves that your eye is still sensible to. As the waves get shorter, you go from red to orange to yellow. Now, you'll never see me pull the metal out of the forge and have it green. And the only reason that happens is that while some of them are vibrating green, there's so many vibrating red and orange and yellow that it's starting to look whitish, right? But when you have something really hot like the surface of the sun, it gives off all the wavelengths of light. It makes a nice smooth rainbow. That's not what this does though. This only gives off a few special colors of light. Now, first we have to understand why it does that. So let's take a look with the board and let me draw a basic atom. This is just an iconic atom, all right? And to draw this, I need to put in the energy shells. So here's the nucleus, and here would be the first energy level, then the second energy level, third energy level. Let's go out to 4 energy levels. All right? So if I have an electron here, and I hit it with enough energy, it might jump all the way up to here. Now, how can it get back down? Well, it could go from here to here, then here to here, and here to here. Or it could go here all the way down to here. It could go here all the way back down to there. It could go from here and then jump all the way back down. So there's a number of different routes that any electron can take in getting back to its ground state. Let's look at these. If it were to say jump from here to here, well, that's not a lot of energy, and it might give off a burst of red light, because red would be the difference, or that red light represents the difference in energy levels. If it jumped from here down to here, well, that's a bigger energy jump. That might give off orange light. I should be careful with that. Might give off orange light, a little shorter wavelength. Let's say it made the jump from here all the way down to its base state. Well, that might be a great deal of energy that it's giving off. And that energy might be represented in blue light. So any atom, which is a complex structure of energy shells, has its very own signature it would give off when we illuminate it with this. For example, the neon light is that. Helium gives off a different light. And if you look at that with a spectroscope, it's an entirely different pattern of lines. And it's the pattern of lines. 2 lines, then a space, then a third line, then a space, then a fourth, fifth, and sixth line, right? Whatever the pattern is, that's what you see when you look at it with a spectroscope. So, how does this play into stuff with stars, right? Follow along. If I were to have a star here, all right, make this edge of a star. Around the star, it's typical that you'll have the gas of which the star is made in a thin, tenuous atmosphere around it. So some of that light, now remember, all the different wavelengths of light are coming through that gas. Some of that light is absorbed by an atom. Those things, those places where it absorbs it, are exactly analogous to the energy levels that spit it out. So every place you have a pattern of a bright line spectrum, you would also have a pattern where it's being absorbed by the gas. So this atom, once it absorbs those few frequencies that it actually can, not all of them, but just the frequencies that it'll get its electrons to do the jumping, once it absorbs those, it will spit them out, but in all sorts of different directions, not necessarily at you. So now when you look at the spectrum of a star, and you have all the colors here, what you're seeing is very specific dark lines in it, and a pattern of dark lines. Specific patterns of dark lines. It's those patterns of dark lines that scientists search for. Because after all, we could take this stuff and see the patterns they make. We could see the patterns of every known atom. We could see the patterns of every known molecule. We can excite them the same way, see what kind of bright line spectra they give off. So when we look at a star and we see the dark line absorption spectra, where that cloud of gas around the star is absorbing those lines, we just have to match the patterns to the known elements and molecules here on planet Earth. And if we can make a match, that stuff is around that star. So every star is acting like a laboratory, illuminating the stuff that is making up the star. Think about that. Every star is telling you, if you know how to analyze its light, what it's made of because of its dark line spectrum. So in the labs, we get a bright line spectrum From spectra looking at stars, we get a dark line spectrum. Those two things match, and we can find out what every element inside a star is, or at least around a star. And we infer that those elements are inside a star. So that's how the spectrum of a star allows us to understand its chemical makeup. Hope that helped. Thanks for watching.